In this class, we study fluid dynamics, especially the Bernoulli equation. To study Bernoulli equation, we have to know what the divergence theorem is. And at the end of this previous lecture, we studied the gradient theorem to prove the Archimedes principle. So with this, we need to consider the divergence theorem first. First, we have to review the differential operator in the vector calculus. This is a position vector expressed in terms of the Cartesian coordinates. And we have a vector field. The vector field means a function that is a function of a position vector. That is called the field. And the field is called the vector field. Its value is a three-dimensional vector. For example, the scalar potential, the potential energy, is a scalar. So this is scalar field. And the electric field, gravitational field, they are a vector field that is a function of position in space. It is convenient to make use of Cartesian coordinates when we deal with the differential operator. It is not required, but it is simple if we use Cartesian coordinates. The reason is that the basis vector of the Cartesian coordinates is constant everywhere. For example, E1 at point X is the same as the E1 point at the origin, and everything else will be the same. So if I take the partial derivative with respect to the first Cartesian coordinates, it's a zero. Is also independent of time. So space-time coordinate relative with respect to the space-time coordinates, the unit vector, the unit basis vector of a Cartesian coordinates, the differential, it's a partial derivative is always vanishing. Let us consider to operate a differential operator to a scalar field first. This is a potential energy, which is a scalar field, and we take the derivative, differential operator called the gradient. This gradient is the sum of partial differential operators. So x component is the x derivative, y component is y derivative, and z component is the z derivative. From the potential energy, we can obtain force, the conservative force, by taking minus gradient. So this is the minus gradient of a potential energy. Okay. So the first component, second, and third components are the negative of the x derivative of potential energy, y derivative, and z derivative, and so on. To carry out explicit computation, it is good to exercise simple problems. Simplest vector vector field is the position vector. Position vector has components xi. The xi is the ith component, ith Cartesian component of the position vector. For example, x derivative, this is 1, partial derivative of x with respect to y equals 0. Partial derivative of x with respect to z equals 0. That means if I take the derivative with respect to xj, then it is either 1 or 0. I equals j, then it is 1. I equals I is different from j, then it is j. So it is delta j is Kronecker delta. In addition, we have one more thing to check: radius. That is a square root of x squared, y squared, and z squared. If I take the derivative r with respect to x, then it is 2 square root x squared, y squared, z squared, and this side we have 2x according to chain rule. So it is x over r. In a similar manner, r's y derivative is y over r, and r's z derivative is z over r. Therefore, r's xi derivative is xi over r, as it is. As a result, if I take the derivative with gradient operator, gradient e1 x, put r in here, gradient of r is e1 hat x over r, 2 hat y over r, and e3 hat z over r. And we have denominator r, and this numerator is just x vector, and r is the magnitude of x vector. Therefore, it is a unit vector along the radial direction. Very simple. So if we make use of these results, we can compute gradient of f r for arbitrary function of r. So gradient of f r, I can make use of chain rule e1 hat and so on. This one, chain rule, and then what's that? Everything has this vector. So this is x over r. So r hat f over dr, as it is. So gradient of arbitrary function of radius is very simple. Divergence. Divergence is the same differential operator, but it is the resultant value is a scalar because it is applied to not to a scalar field but to a vector field, and it collects the first, second, and third component, and we take the derivative with respect to each component and sum them all. This is divergence, and divergence is a scalar field. The next one is curl. We already studied, so let me just pass this. So curl 0 means E rotation. It does not rotate. So let us consider the case. We learned that if a force is irrotational, we can make use of the Stokes theorem to find that the Stokes theorem, curl F dot the sigma over surface is the same as the line integral along a closed path surrounding the surface. Okay? Because if F is irrotational, curl equals 0, so it is vanishing. That means scalar, so it is 0. That means the conservative force integrated over the work done by conservative force integrated over closed path is always vanishing. So from this we can state that the F is conservative, the path independent. In another way, we can show that if there is a potential energy such that force is minus a gradient potential, this is irrotational. How? Let us substitute this curl, the minus gradient curl, this is curl, gradient u. As I already stated, the cross product can always be expressed in terms of a determinant. That is u1, u2, u3, et. And gradient operator, the differential operator. And the third one is gradient u. And take the determinant. We can pull this u outside. In that case, equals differential operator and u is outside. You can see these two rows are the same. And in any case, the two rows are the same, determinant vanishes. Another way to find that this is a vanishing is explicit calculation using Leibniz-Vita tensor. And by making use of the anti-symmetry, if we exchange any two indices, for example, J and K are exchanged, we have negative sign because of the permutation. However, if we exchange the order of a differential operator, it doesn't matter. They are symmetric. So product of symmetric and anti-symmetric vectors, the result is always a vanishing. And this one shows explicitly vanishing. As a result, if we can write a force in terms of a scalar function's gradient, it is always irrotational. If it is irrotational, according to the Stokes theorem, the work done by that force along a closed path is always vanishing. Before we go ahead with the divergence theorem, it is good to know what the current is and how the current is expressed in terms of current density. Current is usually used for the charge current, and in here we are more interested in mass current instead of charge. So it doesn't matter. What appears in here as a rho is a density. Density can be a mass over volume or charge over volume. The second semester, we'll study electromagnetism, and when we study current, the charge density will be, a rho will be expressed as a charge density, that is charge per volume. And right now, we are interested in the mass per volume to be the normal mass density. Okay, current means there is cross-sectional area, flow of matter, such as charge or mass. They are passing through a surface. This direction is a normal, and this direction has non-vanishing parallel component with this flow of matter, flow of mass or charge. So if I allow some time, because they are moving uniform velocity, for simplicity, we assume that the velocities are all identical. In that case, for a short time, there is delta t, displacement of these current, and we have a cross-sectional area. So this is the delta x. So cross-sectional area multiplied by the height will be the volume in which the particles are passing. So why don't we stop right now from 0 to delta t? We have some volume. Inside the volume, we can define a density, either this mass distribution or charge distribution. So mass distribution case mass over volume will be the density. So how much mass is there inside this volume? So delta m will be density times volume. What is the volume? The volume will be the cross-sectional area multiplied by height. What is the height? Height is the velocity times delta t. So rho a v delta t. Why don't you divide everything all together with the time shift? Then I would have mass divided by time. This is current. How much mass, how much charge has passed through the cross-sectional area A? That is current usually. Right now we are more interested in writing phi, that is called flux. Flux is the same as a current. And this current is what? Rho, V, and cross-sectional area. This is current. So current I over flux phi is rho V times A. Here, rho V is written as a current density J. So we have JA, and let us revive the vector nature of the cross-sectional area. Cross-sectional area has magnitude as the area, and it has a direction that is normal to the plane. So if I introduce this, what I would obtain is I would revive the vector nature of the current density because the direction is determined by the velocity of each particle. So, and then we take the scalar product to make the whole thing as a scalar. Finally, I have a good definition for the current density J. That is, if I copy these results, it should have been vector A and rho velocity vector. Therefore, current density is a product of a density multiplied by the velocity. In addition, if I integrate over a surface, the current density with the scalar product with the differential area element over a general surface that may be curved, then I end up with the current I over the flux phi. The density rho is mass over volume or charge over volume. And mass or charge may be consisting of many identical particles. In that case, we can say m is the, if there are n identical particles, then m is the n times single particle mass. For a charge is consisting of n identical particles, then each particle has a charge small q, then I can write it as it is. I substitute them in here, m over v becomes number of particles and single particle mass divided by volume. The number per volume is called small n, and small n is called the number density. So number density, if number density is known, then I can multiply the elementary particles mass, either mass or the charge, to have a density for the charge or density for the mass. As an application, we compute the flux. We have equally spaced particles with the number density capital N of V is distributed over space, and they are translating with the equal velocity along the z3 hat direction with the magnitude V. So we have current density rho V, and rho equals n times, this is mass distribution, so n times m, small m is the mass of a single particle, and velocity, this is the current density. And we are interested in computing the current density is given in here, and v equals to v times z3 hat. And we have cylinder extended space with symmetry axis. Okay, symmetry axis is making a direct about relative to a E3 hat. There's the angle theta. The mass flux phi passing through the upper lid S, upper lid, this surface. So area is this. This is of radius r. So pi r squared, and direction is along this direction and hat direction. We're interested in find out the flux. Then this is uniform, so pi r squared, and the magnitude of the current density is nmv. And then we need to take care of the cosine theta. This one is cosine theta. So it is independent of the azimuthal angle phi. It depends only on the polar angle, that is the angle between the E3 hat and n hat. Next, we consider integral form of continuity equation. We consider a flow of mass is coming out of this volume, and surrounding this volume, the surface, boundary surface, is S. So flux passing through this closed surface, this circle means closed surface, we integrate this differential flux over the whole surface. And because this is J dot this sigma is J equals rho V that this sigma, So rho v dt over dt, this sigma, then what it is. So the sigma is the cross-sectional area, and v delta t is the height. So this is a kind of cylinder with a volume. The volume is v dot the sigma dt. Okay? So this is volume. Volume multiplied by density, that is mass. So the time over delta t. So if we integrate this one, we obtain dm over dt. How much mass is passing through the surface? But right now, this m indicates the mass inside. Then this is passing through the surface. That means mass inside is decreasing by that exactly the same amount, but in opposite direction. So because mass, for example, 1 kilogram is passing through the surface, that means that inside this volume, 1 kilogram has decreased. This is the integral form of the continuity equation. The flux integrated over a closed surface. This should be a closed surface. Okay. So I corrected this one as a circle to close the surface. The current to pass through a closed surface, this is current density. Then the integral over the closed surface represent the time rate of decreasing the mass inside. And we can rewrite this mass as a volume integral because mass is density multiplied by volume. If the density varies depending on the position, we can write it as a three-dimensional integral and integrate over the space, volume, and with the total mass. Okay, so I can rewrite this total mass inside the volume, inside the surface. This is the continuity equation in integral form. Next, we consider the divergence theorem. The divergence theorem is related to the volume integral of divergence of a vector field. That is arbitrary. Any vector field is well-defined vector field over the space enclosed by this closed surface. So we have a surface that is closed, that is the boundary of a volume, and we are interested in evaluating the volume integral over this volume. Volume integral of what? Divergence of any vector field. Right now we are interested in the current density, J, whatever. It's okay. So I'd like to integrate over the volume. The integral can always be divided into many pieces. So why don't we divide? Right now we are interested in some specific volume, but for simplicity, we introduce a sphere. And I would like to integrate the divergence of J over this sphere. And in some case, we can directly compute it, but in order to prove divergence theorem, it is more convenient to divide into many small pieces, and especially into a cubic form. So it has a size delta, delta, delta. So rough surface shows that I have not divided into large enough so that each cube is too large so that it is very rough, but I can increase the number of cuts to find the n number of beans to be infinity, then it becomes smooth and we can recover the whole volume. So let me divide this volume V into many pieces. Vi, this is V1, V2, V3, V4, more than 1,000, million, or whatever. So as large number as possible, keeping this one goes to zero and goes to infinity, and the surface becomes smooth. In that case, the volume integral of this V can be expressed in terms of the volume integrals over these tiny volumes. So why don't we concentrate on a single integral, and we'd like to combine everything all together to reproduce this whole picture. Each tiny volume of Q is infinitesimally small, so delta is going to zero, but we magnify uh, every cube in this form. This is a cube with every side delta, delta, delta. And this volume Vi has a center at x1, x2, and x3, and we see that every side has the width of delta. So relative to the center, that is the x1, x2, x3, the range of x, y, z value varies from this central value by plus minus 1/2 delta along each direction. For example, I can consider these two surfaces, that is the right end and left end of the range of x. If I choose this side, that is a positive side of the side that is perpendicular to the x-axis, then the surface is defined to be this surface can be expressed in terms of an integral over y and z. In the range y varies from central value minus 1/2 to plus 1/2, and z in a similar manner. Here, at this point, the surface toward the positive direction, so I have positive sign along the E1 half. This is along parallel to E1 half. The other side can be parameterized as the double integral over y and z again. However, the minimum point at this point, at the x equals minus 1/2 delta, the surface is heading toward the negative direction. So this unit vector should be minus E1 half. Therefore, this plus minus mean indicates that the surface that is perpendicular to x1 axis is positively directed for S1 plus and negative along the negative direction for S1 minus. In a similar manner, S2, S3 plus minus are also given by the areas delta squared and directions are plus minus x, plus minus y, and plus minus z directions, respectively. Finally, let me compute the divergence J inside a single beam. This is a three-dimensional integral, a volume integral, and divergence is the sum of x1 current density's first component, second, third component, and we have taken the partial derivative with respect to each component, 1, 1, 2, 2, and 3, 3. If we consider the first term, that is the derivative of g1 with respect to x1, I can integrate, because it is a derivative, I can integrate over x1. After that, I end up with the two-dimensional integral over the yz plane. However, the j1 differential is integrated over x1, same thing. So the answer is j1 exactly. However, I have to substitute the upper limit of x and lower limit of x. Upper limit of x is added or substituted in here, but lower limit should be subtracted in here. So it's negative sign. However, if I return to the previous page, the surface that is perpendicular to x-axis are positively directed on the S1 plus, but at the minimum point, that is at x equals minus 1/2 delta from relative to the center, it is negative direction. So this one compensates. This negative sign comes from the scalar product between the current and the differential vector element that is directed outward from inside the cube to outside. This opposite direction. So this negative sign can be observed by replacing this one as an integral, because this sigma has its own sign containing. This sigma contains the negative sign in it. If I sum these two, I have the same integrand, and then surface is S1 plus and S1 minus. In a similar manner, the J2 component and J3 components can also be expressed as a J delta D sigma, and the two surfaces are along the y perpendicular to the y direction and perpendicular to the z direction. So all six faces of the surface integral can be carried out with the same integral. If I sum everything all together, it is just a closed surface of the cube VI. And the integrand is J dot D sigma. And now it is a closed surface, so I put the circle on it. As you can see, the divergence, the volume integral of the divergence for a single cube is the surface integral over the surface of the single cube. So let us combine everything all together. I can collect these one to reproduce the whole structure. What I have done is just a single integral. So when we combine nearest to neighbor, when they meet together, this overlapping area appears. And the amount of integral is exactly the same. However, because although J is identical at this surface, the normal vector, the sigma of this surface and the other surface that are to be combined are exactly the same in magnitude but opposite in sign. So that means they cancel exactly. So after we sum the two nearest beings, what we end up is the total integral of the volume integral. That's fine. As far as the surface integral is concerned, the overlapping surface disappears and the resultant surface integral is over the surface of the total of the volume. In this manner, we can combine the volumes and surface recursively to reproduce the original volume and surface. As a result, the volume integral for the divergence volume integral, it was divided into many pieces, and then we have found that the surface is, this closed surface is identical to the surface of the original, the boundary surface of the original volume. Now we can apply this one to modify the integral form of the continuity equation. Previously, we have obtained the integral form of the continuity equation, and that is this one. The current, we have computed the flux coming out of a closed surface. So I have to replace this one as a closed one too. So I have replaced this one. So added the missing circle here. It is closed surface. So flux is coming out. Then this flux means the time rate of decreasing the mass inside. So this is positive. Mass decreases is negative. So I have to put the positive sign. And mass should be replaced with the density integral over the volume. And I have inserted this time derivative inside because the volume, this position is independent of time. So this time derivative is applied to the partial derivative, and then is moved to the left-hand side. However, it is a surface integral, and it is volume integral. Fortunately, we are now able to replace this surface integral as a volume integral by using divergence theorem. So it is divergence J. So if I combine both of them, it's like that. This integral is always vanishing now, and for any volume. So let me decrease this volume into a tiny region with a radius epsilon, and take the epsilon goes to 0, but it is not equal to 0. It's infinitesimally small, but it is a non-vanishing. Then, such as in the small area, the integral should be frozen to be a constant value. So I can factor that out of the integral. But still, this region is very tiny. However, it is not 0. So it is a kind of variable. This one multiplied by non-zero value, arbitrary non-zero value is vanishing. That means that this one is vanishing. That is the differential form of a continuity equation. So let us apply this continuity equation to an incompressible liquid. Incompressible liquid, if I apply compression stress, there is a no strain. Strain equals 0. So stress over strain is the bulk modulus, negative value bulk modulus. So because it is 0, it becomes infinity. Bulk modulus is infinity. That means there is a no delay, there is a no change in shape That means if I push, the size is invariant. Then mass is invariant, volume is invariant, density is invariant. So everywhere density is invariant. Everywhere. That means independent of time, independent of x. So rho is a constant. In the continuity equation, we have divergence J plus round rho round t equals 0. Because this is constant, independent time and space, so it is vanishing. So divergence J is exactly 0. The current density is rho times V, and rho is invariant. V may change. Divergence J equals 0. Divergence J equals 0. Its volume integral is 0 always. And surrounding that volume, I can rewrite this one by making use of divergence theorem as a current times this sigma over closed surface is also 0. So if the mass current is flowing along a kind of variable radius 2, I can choose some volume, and this side is a fixed. Flow comes in and comes out. And if I compute this, what I have to do is current times J dot this area and plus J dot this area, A prime, J prime. And this one should be 0. Here, the normal vector, this current J is flowing in the same direction, normalized to be, and then the normal vector is opposite. So if I replace them in terms of scalar function, current and area with negative sign plus J a positive sign, equals 0, something like that, prime prime. So JA equals J prime A prime. But because J is a product of rho times velocity, I can substitute in here. So rho cancels because rho is constant. Rho is constant. So is a VA equals V prime A prime. This is the result of the continuity equation for an incompressible fluid. As a result, there's a wide area, small cross-sectional area, then VA product should be the same at here and there because it is closed. There are two open ends. There's a wider, narrower, so it is slower and faster. So their product, VA and VA, is a large velocity, small area, large area, small velocity. So this product is invariant. This is the consequence of the continuity equation to the incompressible fluid. Bernoulli's equation is a direct consequence of the uh, continuity equation applied to incompressible fluid. A fluid is moving along this tube with a variable cross-sectional area. We have a wider cross-sectional area on the left end, on the right end. So we have a smaller cross-sectional area. And we have rho equals constant and mass is invariant. That means rho equals volume, mass over volume. It is not compressible, so volume is strictly proportional to mass. So if there is no mass lost or mass gain, then the volume should be preserved. If the fluid is coming into this left end and coming out of the right end, then the amount of fluid, that is volume, moved during the time delta t should be cross-sectional area multiplied by the distance, that is a velocity, times time. So cross-sectional area multiplied by v delta t, that is a delta v, on the left side. And right side, the cross-sectional area is smaller. Then, to keep the volume the same, the velocity should be bigger. So v delta t, and area is small, something like that. But this is a conservation of mass, as conservation of volume is due to the incompressibility of this fluid. So, why don't we consider the energy lost? This amount of mass has disappeared from here, so I have lost the energy. The energy consists of the total mechanical energy, and total mechanical energy is the sum of the total kinetic energy and the potential energy. The left hand, because the motion is from the left to the right, this has been disappeared because we have lost some energy. Kinetic energy is 1/2 mv squared, 1/2 delta m. Delta m is delta m equals rho delta v, right? mv squared. At position 1, I have subscript 1 to indicate the left-hand side. And mgh, the potential energy, gravitational potential energy with mgh. So I have rescaled it with this density rho and volume. So the same, and we have negative sign because we have lost this amount. On the other hand, this side we have gained. Gained what? Kinetic energy 1/2 mv squared, but the velocity is different. This velocity and mgh height is different in general. So this is h2 and h1, and there will be the shift to with delta h, that is h2 minus h1. In addition, this is the just added lost energy and gain, but there is another, because they are in equilibrium with outside. Outside has some pressure. We have pressure P1 and pressure P2, depending on the situation. If there is nothing other than atmospheric pressure, then we can ignore the atmospheric pressure difference at two ends. However, if there is some external pressure on it by pump, then we cannot ignore this one. So we attach P1 and P2. But the pressure from the outside, on the left hand side, the force from the outside is in this direction and displacement is parallel. So the amount there is the work delta W done by the external force to the system. So this is a P1 delta V, that is the gain of the energy to the liquid. In here, the pressure is the same direction, but displacement is to the left. That means the work done by the external force is negative. That means the liquid has carried out the work. So this is an input, and this is a P2 delta V minus will be the output. So we have to consider all of them together. The work from the outside is the gain of the energy, total mechanical energy. So if I sum everything all together and rearrange the terms, everything with the subscript, single subscript on a single side, we find that P1 plus 1 half rho V1 squared rho GH1 equals a P2 plus 1 half rho V2 squared plus a rho GH2, something like that. So pressure plus 1 half rho V squared plus rho GH. This is constant everywhere. I cannot change this rho. I cannot attach the subscript for rho because it is incompressible fluid. Rho is invariant inside everywhere at any time. So Bernoulli's equation can be applied to find the time to evacuate all of the water in a container. On top side, we have a water level of H. We have a wider opening. However, we have a very small opening with the cross-sectional area small a. Then we can apply the Bernoulli's equation. And here we do not apply any additional pressure on it on either side. On both sides, the only pressure on it is a atmospheric pressure. They are almost the same, so I can ignore this amount. And 1 half rho v squared. This I indicated with the denoted by U as the surface water level velocity to downward, and the velocity of water coming out of this small hole with the cross-sectional area small a is capital V. In here, the potential energy difference is a capital H, so I should have added the rho g h, but it is 0, so it's ignored. This relation gives we can eliminate this v in here. Is that what is that? The continuity equation. AU equals VA, right? From this relation, I can eliminate capital V in here. So I find it is all expressed in terms of small u. And small u is actually the time derivative of height. Small u is the time derivative of height. Therefore, we can find this equation of motion is a one dimensional, the first order differential equation with respect to h. I can separate them into two pieces depending on h only and depending on t only. And we can see it is just a dh over square root of h. If you know how to integrate, everything is done. Sure. The constant multiplied by a time differential. So using this integral table, I can integrate over both sides to find the final return. We can make use of the continuity equation. Okay, when we derive the continuity equation, we quickly obtain this is a 0. Or why don't you carefully think about why it was possible? This method is used in various ways, and when we derive the four Maxwell's equation by making use of Gauss law coming from the divergence theorem and the Stokes theorem for the Faraday's law, you will find that it's quite useful. This way of derivation is quite useful. And these are examples of application of the divergence theorem for the Gauss law. And later we will review this for the gravitational field. And in next semester, we will apply this to the electric field that represent the Gauss law. And at the end of the day, you will find that very interesting function that is its integral is just one. And if you multiply this one to another function, you will get the value at 0. But if you replace with the x minus y style, then you end up with, if you integrate over y, you end up with the result with the same function, except that the argument is replaced with x. That's quite interesting function developed by Dirac, and it is called the Dirac delta function. And in mathematical sense, it is a nonsense. However, physicists developed this, and it is a kind of distribution. It is integrable function. It is not a function because it is divergent and a pointwise divergence. However, it is integrable. What a nonsense it is, but it is physically absolutely correct idea. Okay, that's it for today.